Hi guys, StupidSimple here, where I take problems that make me feel stupid and try and make them simple. Today, I'll be talking about the differentiation of trigonometry and the function ln. So in my last few videos, I've covered a few different rules with which to do differentiation. Power rule, chain rule, product rule, quotient rule, those kinds of things. And in those, I've used some examples which have involved cos of x, sine of x, and ln of x. And I've shown these in examples and differentiated them and just kind of told you to believe me when I use them, but I thought for the time being it would be a good idea to at least prove that these do differentiate to the things I've told you they differentiate to, so the next episode we have a complete understanding for what we're doing in order to do a full group of many differentials together. So let's get started. First things first, I'm going to prove to you that the differential of sine of x equals cos of x. I'm doing this first because I can just go one to the other, but it really doesn't matter. In order to prove this, what I'm going to need is a definition. Well, actually, I'm going to need three. First things first, I'm going to need you to know that sine of something, let's say A, plus something else, let's say B, this is known as a double angle formula, is defined as sine A cos of B plus sine of B cos of A. Excuse my handwriting here. So, sine of A and B gets a sine A and a sine B, and a cos B and a cos A. That's just a definition that you may just need to know by parafashion, just as a definition by itself. I'm also going to ask that you know that you are comfortable with the following definitions that we have for small angles. At least we have sine of x divided by x equals 1. And that we have cos of x minus 1 divided by x, that's the minus 1 divided by the x as well, equals 0. These are parts of the double angle formulas, and these are actually limits. Limits where x tends to 0. So these are very small values of x for both of these. That's the limit as x goes to 0. But they're useful to know for this definition. With these three things in mind, we're ready to go. So what we're going to do to prove that sine differentiates to cos is just use the definition of differentiation, which we covered in our first video. If you're not comfortable to that, I'll link it below. But you'll remember that our differential definition was that d by dx of some function of x equals the limit as h goes to 0 of f of x plus h minus f of x all divided by h. That was our definition. That's what differentiating is. That's the explicit way of doing differentiation. What we're going to do here is exactly the same, except for our f term that we're differentiating, we're going to throw in sine. I'll use some colours here so things are a bit easier to see, but I hope this will be simple enough to follow along. Let's start over here. Let's say our function of x equals sine of x. And we want to find f prime of x, or d by dx of f of x, or we're differentiating our function of x, which in this case is sine. Therefore, f prime of x is f of x plus h over here, and therefore let's call this sine of x plus h. From that, we're going to minus our function of x, which is sine of x, and we're going to divide the whole thing by h. Okay? So the first thing we're going to note here, in order to do something with this, is that this term right here, the sine of x plus h, this one, all of this, is just the same as our top line up here. It's sine of something plus something. So we're going to substitute x and h where I put a and b up here before. So let's do exactly that. Let's come down and say f prime of x is equal to sine of a. Let's do a little bit here. Let's say a is blue and b is red, just so we can keep up with color coding. So it's red there, and blue there. So therefore, f prime of x equals f sine a, our blue color, is x, times by cos of b, our red color, and to that we're going to add a sine of b, our red color, multiplied by a cos of, oh, I've been a dummy. These are not b's, these are h's. And we have a cos of x here. So that's the double angle formula. We now, instead of having a sine of x plus h, we have just sines and coses of one thing. Going back to our original f prime of x over here, we are then going to take away the sine of x that we put down here. So that's just going to come right down here and say minus, I can write better than that, minus sine of x. And then our definition also has that division by h. So we'll take an h all the way over the bottom of all of these. From here, we're going to try and do a little bit of rearranging, starting with, we'll notice that we have a sine x by itself on the edge here, and our first term also includes a sine x. So we're going to try and group those together. So we'll say f prime of x equals sine of x multiplied by cos of h and from that we're going to take away 1. So what I'm doing here is I'm taking my sine of x at the front here and using my cos of x to get these two terms. But then if I'm doing a bracket, sine times two things, I can then take my sine here as a minus 1 and sub it in for this minus 1 down here. Okay? We then have our other term, plus sine h times by cos of x. And again, all of that is divided by h. But to make things a little bit, should do that in red. But to make things a little bit more readable, I'm going to just put both of these as two different things divided by h, just so you might be able to spot what I'm going to do to our terms here. Because we have an addition, so these are two different things, but they are both still divided by h. If you look at our definitions up top, up by here, starting with sine x divided by x. Again, this is a limit as x goes to 0, but if you'll remember the definition of our differentiation does have an implicit, or I should have been explicit and wrote it down the whole way, but we are looking at a limit when h tends to 0. And since h is on the bottom here, if we consider, say, our second term for now, this one here on the right, let's get away some of these arrows so things are a bit clearer. If we look at our second term, we have a sine h divided by h times something else, times cos x. But, for the time being, let's just ignore the cos x because it's a multiple and it's in terms of x, not in terms of h, so it's kind of different to what we're dividing by. Oops. So we have a sine h divided by an h. And if we look at our definition up by top, when h, or x, is of sine x divided by x, we have a 1. And we have the exact same situation down here, where we have a sine h divided by h. So therefore, that means that this term equals 1. Similarly, if we look over to the left hand, the first term, this one, we can see that we have something of x and something in h. Again, because these are multiples, I'm just going to move over the division by h just underneath the cos h minus 1. And again, we're looking at a limit as h goes to 0. And if we go back to the top, we have cos of something minus 1 divided by that same something in this limit as that thing goes to 0. The whole term, cos x minus 1, all divided by x, goes to 0. And therefore, this term down here equals 0. Since this term equals 0 and it's multiplying this sine x, the whole thing goes to 0. And therefore, we can say that our f prime of x equals 1 times by cos of x, which is just cos of x. And there we go. That is proof, using the definition, that sine of x differentiates to cos of x. I hope that made sense. If you didn't quite follow any of that, let me know. I understand that just asking you to believe me when I say that the double angle formulas at the top and the limits are what they are can be a bit of a leap in logic and a bit of a leap of faith. That's absolutely fine. If you're not comfortable with that, let me know. I'll do a video dedicated to them specifically. But for now, if the rest of this made sense, we'll move on. And we'll start with cos x, because that's the next step to go, I guess. That's the next thing to do. So we're going to use the exact same logic, but I will tell you now that cos of a plus b as a double angle formula is arguably easier, arguably harder, depending on how you look at it. Because it's just cos a times by cos b minus, this is where the difficulty is, it's the terms of both causes on the left, so they're easy to remember, but the minus means that we have to remember order, and it's minus sin a sine b. The limits before are the same, so the limit as x tends to 0 of sine x divided by x, that still very much equals 1. And the limit as x tends to 0 of cos x minus 1 divided by x equals 0. Exact same as before, and we're going to do the exact same logic, but I just want to prove to you that these things are indeed true. So let's get started. Let's do a bit of color coding. Let's call our A's in blue and our B's in red. And let's say we have our f of x equal to cos of x, and we want to find f prime of x. We will use the definition as before, and therefore we have cos of x plus h minus cos of x, and we have the whole thing divided by h. Again, we will expand the double angle formula here with in terms of x and h instead of a and b. So therefore, oh, and before I forget, we'll say that this is the limit as h tends to 0. That is implicit whenever I do the formula here. If I forget to put it in, tell me, and I'll change that in post. If not, and if you're comfortable knowing that these things are just here, that's great. If not, tell me, I'll be more strict with myself in the future as well. Either way, moving forwards, f prime of x equals the limit as h tends to 0 of, we have cos minus sine. See if you can fill in the brackets for yourself quickly, just so if you understand what's going on here, just as a little bit of a sanity check. Okay, if you've had a chance, great. If you haven't, that's okay. We just want 1x on the coses and 1x on the sines. We also want an h in the coses and an h in the sines. Because of the way these things multiply together, technically you can have an h on the left and an x on the right. That's absolutely valid for both of these. But just to keep with convention and notation, I'm going to stick with x's and h's in this order, although it doesn't really change much at all. Following along using the definition, we have our minus cos over here, and therefore we're going to minus a cos over here. So we're going to do exactly that with minus cos of x. Terrible exchange. We're going to divide the whole thing then by h. Cool. So now we're going to factorize again as we did before. We're going to say f prime of x equals the limit as h tends to 0 of, we have a cos x here and a cos x here, so those are the two things I'm going to factorize together. So we have cos x, we have a multiple of cos h here and a multiple of minus 1 here, so we'll say cos minus 1. Again, see if you can fill in the brackets, or the bracket, it's an h. And then we're going to minus our other term, this one. So that's minus sin x sin let's keep things consistent and put that x in blue, minus sin x sin h. And again, the whole thing gets divided by h. I'm going to do the same trick I did before though. Instead of dividing by everything by h, I'm going to separate these two terms into two terms. One here and one here. And in fact, I'm going to be a little bit more specific just for sake of how our eyes are going to read this. I'm going to divide both of these by h below the h terms. That's absolutely valid to do as long as they are still the same term and multiply the way that trigonometric functions do, which is not a problem which shouldn't really be a problem that you come across until university level maths, where things don't multiply the way these do. But for now, we're going to put the h's below the other h's, the red below the red. We're going to then look up and see that our definitions up here are used again. Specifically, we have a sin h over h here, and this is where the limit of h goes to 0, so therefore this definition is valid. Sin h divided by h equals 1, and we have that cos h minus 1 divided by h, as up top before, when the thing that's in the cos and is being divided by is or is close to 0, this will then equal 0. Therefore, we can say that f prime of x equals 1 times minus sine of x. Or in other words, minus sine of x. And there we go. We've differentiated cos and sine of x, both together using the definition. I would recommend, as an exercise to yourselves, trying the differentiations of minus sin x and minus cos of x. They're just ever so slightly in terms of arithmetic because of the way that the negatives work, but they're more or less exactly the same logic that goes along here. You should find that if you differentiate minus sine x, you're going to end up with cos of x, and if you differentiate minus cos of x, you will end up with sine of x. Give it a go yourselves in the free time, and let me know down in the comments if you have any problems with that at all. I'll gladly do a dedicated video to those two examples myself. But in the meantime, I think we're pretty well equipped now to go to the last example of this video, and then we'll be pretty well equipped to look at, well, pretty much any differentiation that I'm going to want to throw at you for the time being. But this one is a bit trickier. It's easy to write shorthand, but the proof of it is a little bit longer, so it's best we get started now. The differentiation, or d by dx, of ln of x. This is going to take a minute to prove, but we'll do it together. First things first, in terms of thinking what it is, ln of x is the opposite of e to the x. If you think e, the exponential function, starts at a point and goes really, really big, ln of x starts quite low and travels out and sort of tends quite flat to one point. This is a pretty bad drawing, actually, to be honest. What I want you to take away from this, that's more like it, is that ln of x trails out, and in fact the e to the x and ln of x are opposites with each other. So much so that if you put e inside of ln, i.e. you act one on the other, that equals 1. Equally, if you put e to the power of ln of, say, x, you will get x. The two cancel one another out. That will be useful later on. I'll just keep ln of e equals 1 here because that's the one that specifically we're going to care about later. This is kind of the only definition that we're going to need in order to prove the differentiation of ln of x, which, as I've used before, I'll write up here just so we can see when we're done. It's just 1 divided by x. It's a very simple thing, but it takes a minute to get there. So let's do it now. We're going to start by using the definition as we have before, the limit as h tends to 0 of f of x plus h minus f of x, all divided by h. In this case, f is our ln function, and therefore we have the limit as h tends to 0 of ln of x plus h minus ln of x. And we're going to divide all of that by h. Now, the way that ln works, it has a few rules associated to it. Firstly, that if you have a function of ln, i.e. the one on the left here, and you're minusing a function of ln from it, you can instead divide by that. What I mean is, if you have something like ln of x In fact, let's be colourful here because that's easier to see. If we have ln of x, and from that we minus ln of y, for instance, that is equivalent to saying ln of x divided by y. Okay? Therefore, this top line here, the numerator of our definition, is equivalent to writing the limit as h tends to 0 of ln of x plus, actually let's go blue to make things even clearer, of x plus h divided by x, where x plus h, our blue thing, is on top here, and x is our red thing here. That is then also, according to the definition, being divided by h. We can rewrite x plus h divided by x, the thing inside the ln, in here, as the limit as h tends to 0 of ln of 1 plus h, squeeze over a little bit, divided by x, all divided by h, because x divided by x is 1 and h divided by x is h divided by x. This is useful because now we have something divided by x and we can sort of play around with our figures a little bit now. It's going to be useful here. I'll put in blue, say. We have the function h divided by x inside of our ln, and I'm going to just instead call that t. We can call it any number we like because it's just something divided by something else, and we can rearrange that. That's absolutely valid. For instance, we therefore have that h is equal to x times by t, according to what we set t as. Remembering that we're looking at a limit as h tends to 0. Therefore, as h tends to 0, this is 0 and being divided by something else, so it doesn't matter what this is, this whole thing is going to go to 0. And therefore, that's going to make t go to 0. Based on the way we've set it up here. So, if we have something else going to 0, we can change the way that we're asking our equation, the way that we're looking at things. Let's substitute t wherever we see it's valid and use these two new things inside of our new equation over here on the right. Let's start by saying we want the limit as t goes to 0 of ln of 1 plus t divided by xt. We can rearrange this into the limit as t goes to 0, because you'll see as t goes to 0 we still have a t on the bottom right here, and that's not quite fun to work with, but we have some workarounds. Let's call this the limit of 1 over xt times ln of 1 plus t. Much like we have a rule up top right here with when something is subtracted from a ln, we have another rule for when something is multiplied or multiplying a ln. If we have, say, an x multiplying a ln of y, then what we have is a ln of y, let's keep color codes, then what we have is a ln of y to the power of x. Again, this is a standard rule, standard definition, but it's useful here because you can, oh, that's meant to be an xt as well, if anyone of you caught that out, well done. you can see here that we have a 1 over xt multiplying our ln of 1 plus t. And therefore we could define that as the limit as t goes to 0 of ln of 1 plus t all to the power of 1 divided by xt. Because of the way that powers work now separately, where we have some x to the power of, let's say, a b, that is equal to x to the power of a to the power of b. What that means is that here, instead of 1 over xt, we're going to say that's the limit as t goes to 0 of ln of 1 plus t to the power of 1 over x, throw another bracket in there, to the power of 1 over t. Okay? And even more so for sake of consistency, because again, with the way that multiplication works for algebra like this, I'm going to swap those two around. I'm going to say 1 over t here and 1 over x here, just for making what I'm about to do a little bit clearer. So we can then use the rule that we defined here, the power rule with the ln, backwards. Since we have something here to the power of 1 over x, we're now going to throw that back into the front. So what we're going to say is that this equals the lim, or limit, as t goes to 0, of 1 over x times by ln of 1 plus t to the power of 1 over t. Those of you who remember at the very start what we're aiming for, ln of x equals 1 over x at the top left, you can see we're getting very close, and we are. What we're going to do now is we're going to see that we're taking a limit in t. Okay? We're going as t tends to 0. But in front of our term, we have an x. X and t, they are related, it's sort of. There's a relation of h there, but they're not really interacting with each other in this case. So we can instead say that we're looking for 1 over x times the limit as t goes to 0 of ln of 1 plus t to the 1 divided by t. And again, ln itself is not a function of t, it's just a function, so we can throw the limit even further inside. Let's come over to the left again, and we'll say that we have 1 over x times by ln of the limit now as t goes to 0 of 1 plus t to the power of 1 over t. Finally, this here is a known value. The limit as t goes to 0 of 1 plus t to the power of 1 over t. This is exactly e. This is a known thing. Again, this is another case where I'm going to ask you to trust me. I'm proving something that I asked you to trust me on before by saying trust me on this as well. If you'd like a full video going into why this is the case, please let me know down in the comments. I'll be glad to do a video on that as well because it's quite fun. But for the time being, trust me that the limit as t goes to 0 of 1 plus t to the power of 1 divided by t equals e. That means that our term now becomes 1 over x times by ln of e And if you'll remember way back at the start of this example, somewhere up here, yep, up at the top right here, ln of v equals 1, because they cancel each other out, because they are opposites in what they are. Therefore, if this equals 1, our final term, our differentiation of ln of x equals 1 of x. I realise that was a bit more of a painful and a bit more of a complicated video than I've done before and others like it, but I hope this made sense. I hope you enjoyed, and I hope you learned something from this, and I hope you feel a little bit more ready to go into as much differentiation. We have as many tools as we could possibly want to do any differentiations we want. If there's anything that you think I've missed, or there's anything you would rather I go into specifically about this as well, please tell me, let me know. I'll be glad to make videos on all of them individually. In the meantime, I hope you learned something today, and I hope you enjoyed. And maybe, just maybe, you found that simple, right?